respected dignitaries on and off the dais, good afternoon to all. So today I am discussing a small topic, that is application of fuzzy logic on FMECA, failure mode effect criticality analysis studies on LNG terminals, especially LNG unloading facilities. So these are the agenda of my presentation. I will just give an introduction about the different hazard identification and quantification tools. I can mention some of the limitations of these tools, and with the help of fuzzy logic and Bayesian network, I am trying to rectify some of the deficiencies of these tools. And today I am especially discussing on the application of fuzzy logic in FMECA, failure mode effect criticality analysis. Then I will be discussing on what is FMEA, what is FMECA. Majority of you are aware about it, and I will be discussing a small case study, application of FMEA and FMECA on ABS. All of you are familiar what is ABS, and some of the limitations of this RPN connected with FMECA are cited in certain literature. I will highlight some of the limitations of this RPN. Then I will show you a 2 minutes video about natural gas value chain. It's a very wonderful video, so please give some more time for the playing that video. Okay. Then application of fuzzy, and then I will discuss another case study, that is application of fuzzy logic on FMECA on LNG unloading facility. So I am having more slides, and I will be giving just important point in that, and later on if somebody is interested to interact with me, we can interact. Okay. So these are the hazard identification and quantification tool. PHA stands for process hazard analysis, but here I am telling it as a preliminary hazard analysis. Then FETI, also known as Dow index, fire and explosion and toxicity index, also known as Dow index. Then HAZOP, hazard and operability study, the well-known hazard identification tool. Then fault tree analysis, event tree analysis, bow-tie analysis, layer of protection analysis, and failure mode effect analysis, FMECA, failure mode effect criticality analysis. Today our focus is FMEA and FMECA. So this is a worksheet of fire and explosion index. So all of you are familiar, this is a HAZOP worksheet. Then this is fault tree analysis. In fault tree, the major problem that we are facing, we need to get the failure probability data of basic events. But unfortunately, in India, we are not getting that data. So we are laying on the data from CCPS data, ORIDA data, etc. for our fault tree analysis for estimating the top event probability. And we have developed a database for the failure probability values of the basic events for conducting fault tree with the help of fuzzy logic by using expert elicitation. Then this is a typical event tree. Then bow-tie analysis. Bow-tie analysis is a combination of fault tree analysis and event tree analysis, and there will be a center event that is called a critical event. In fault tree, that critical event will be the top event. In the case of event tree, that critical event will be the initiating event. Then of course the layer of protection analysis. LOPA also have certain limitations. With the help of by integrating fault tree and LOPA, we can identify the limitations of LOPA. So due to lack of time, I am not discussing all those things. Then coming to our topic, failure mode effect analysis and failure mode effect criticality analysis. So if you are having a system is having a number of components, and there are different failure modes for different components. So in this FMEA analysis, what we are doing is, we need to identify the failure modes of different components, and then what will be the effect of that failure mode on the system. So that analysis is simply failure mode effect analysis. And when you are introducing a criticality aspects into that, it is called FMECA. That means which element or which failure of which component will be more critical to your system. That analysis, we are simply calling it as FMECA, failure mode effect criticality analysis. So what I have mentioned is there in that slide, and this is the FMEA worksheet. Then a simple case study on ABS system is there. So all of you are aware what is ABS. ABS is used in our car. It is anti-lock braking system. So it is something similar to a SIS, safety instrumented system. A safety instrumented system which consists of 3 parts. Which are the 3 parts? One is a sensor, other one is a logic solver, and third one is a control element. Okay. So here in this ABS also, there are 3 elements. One is sensor, second one is a control, second one is a control valve, and the third one is Third one is the logic solver. So sensor S1 and S2 to measure the speed of two front wheels. So what is the purpose of this ABS system? To avoid skidding. When it will skid? When the front wheel is very less when compared to that of the rear wheel, skidding will happen. So this system or the ABS is it will avoid that. Okay, so for that it will sense the speed of the front wheel as well as the speed of the rear wheel, and it will feeding into a microcomputer, and accordingly the microcomputer will give a command to open the valves to reduce the braking effect. Okay. So this is a sample FMEA worksheet on ABS system components. So I'll just discuss the first one. A front wheel sensor S1 or S2 is no S1 or S2. The failure mode is no output signal, and the failure effect is microcomputer will assume that one wheel has stopped and will send a signal to open the corresponding valve, and partial loss of front wheel braking. So similarly, for each component we can find out the failure mode and the failure effects. Then if you are able to know the frequency or the probability of occurrence of that failure mode, we can classify. There are so many standards which will give you the classification for this frequency class and its severity class and then non-detection class. So if you know this classification, we can estimate one number that is called RPN, that is risk priority number. Okay, in FMECA, risk priority number is very important. We need to calculate that, and depending upon that value, higher the value, the higher the risk will be there. So we need to focus on that particular component, that is RPN. But in this table, you can see that when you are estimating, we will get same values. So in a system, you may get similar values. So that is the problem highlighted by the researchers, how we can address that problem. So some of the limitations of conventional RPN mentioned by certain researchers are mathematical formula for calculating RPN is questionable and debatable. Conventional RPN is calculated as the product of OS and D. In the morning session, you could see a very nice risk matrix. So in one axis frequency is there, and the other axis severity is there. So if you know the frequency class and severity class, we can know the risk level, whether the risk is low, medium or high. So similarly, this RPN is the extension of that. One more parameter is coming into that. That is nothing but the non-detection. So if you are simply multiplying these three, it is a wrong concept. So in one of our paper, we established that that concept is wrong, but somebody, for simplicity, it is introduced in that way. Okay, so by using fuzzy logic, we can solve this issue. Yes. Application of fuzzy logic to rectify the limitations of conventional RPN. Okay. So this is a video related to natural gas value chain. I am not showing this thing, but at the end I'll play this thing so that we can complete the entire proceedings. So issues associated with the natural gas operation. Major issues associated with the natural gas operations are loss of containment from the storage tank, loss of containment during transportation through sea, and loss of containment during unloading and leakage during distribution. So these are some of the accident statistics. Then once there is an accident happens, so we can model what will be the impact with a lot of software like Safety, FAST, then Aloha, etc., etc. Then I'll be focusing on only on the unloading part of this terminal. So this is an unloading jetty, and this picture is taken from Petronet LNG Kochi, and these are the unloading arms. Working. Okay. So this is a video related to an accident associated with the unloading operations of LNG terminal. Then this is brief description of unloading facility. I'm not discussing in detail, and the details are available. And I will show you one paper that can be downloadable. In that paper also these details are available. And there are so many parts for this unloading arm. And these are the various parts of the unloading arm, and we conducted the failure mode effect analysis for that particular unloading facility. I'm just showing only a sample, and there is an exhaustive list of different parts of the unloading arm, and the failure mode and its effects are also mentioned. It is available in one paper, and I will show you that paper also. Then accordingly, yes? Failure, sir. Okay.
What was the failure and what was the finding?
Yeah, sir. The foundation bolt, then shear failure, then collapse of the arm. That is one failure. Similarly, pantograph cable.
For the Renjith Kochi case.
Kochi case, these are the failures. In that, around 45 component failures we have identified. It is listed, and 5 are listed in this table. The details are there, and full details are in that paper. Okay, this is that full list of that unloading, that failure of the different components of the unloading facility. Then we need to identify the frequency of that failure. Then we need to classify it is coming under which class. Then we need to identify the severity class and then non-detection class, and then we can estimate the RPN, risk priority number. And in majority of the case, we will get the same RPN value. So that is a problem we need to rectify with the help of fuzzy logic. Okay. So for that, so what we are doing is, in the earlier case, all are the crisp values, but here with the help of fuzzy logic, we will make the function as a continuous function. So okay, this is the way we are doing it, and so for doing this analysis, we utilize the MATLAB fuzzy toolbox, and the analysis is carried out by using fuzzy linguistic variable for the frequency or the occurrence, then severity and non-detection, and then we are using then if-then rule basis to interconnect these variables to reach a fuzzy RPN called FRPN value. There are 3 inputs, that is occurrence or the frequency, then severity, detection, and we fuzzify all these inputs, and we will get a output, fuzzified RPN, FRPN, which will rectify the problems of the conventional FMECA. So these are the rules, and this is the rule viewer, and finally we will be able to prioritize it in a better way. So as a conclusion, the proposed fuzzy FMECA method was invented to overcome the deficiencies of traditional FMECA techniques that relied on RPN, and the analysis was carried out by using fuzzy linguistic variable for occurrence, severity, and non-detection, and then using if-then rule base to interact these variables to reach a fuzzy RPN or FRPN values. So there are so many other limitations cited in the literature that also rectified, and these are the 2 publications on this particular area. The left paper, that is application of fuzzy failure mode effect criticality analysis on unloading facility of LNG terminal, that is what I discussed, and the other paper is fuzzy FMECA on LNG storage facilities, published by our research group.